Okay, so we have a physics PhD qualifying examination practice problem. This is number 4 in the classical mechanics domain. So let's begin. A torque-free rigid body has principal moments I sub 1 less than I sub 2 less than I sub 3. No external torques act on the body. Part A, write Euler's equations. Okay, so this is a rigid body dynamics problem. For part A, Euler's equations in the body fixed frame aligned with the principal axes. The angular velocity is omega equals omega sub 1 e sub 1 hat plus omega sub 2 e sub 2 hat plus omega sub 3 e sub 3 hat. The angular momentum is L equals I sub 1 omega sub 1 e sub 1 hat plus I sub 2 omega sub 2 e sub 2 hat plus I sub 3 omega sub 3 e sub 3 hat. And for the torque-free motion, we have this derivative L with respect to t in space equals 0. A derivative in the inertial frame and the derivative in the rotating body frame are related. Okay, by this dl dt space equals dl dt body plus that w cross L. Since the external torque is 0, the dl dt body plus w cross L equals 0. And if we take the cross product of w cross L, we set this up with this, we get this quantity I sub 3 minus I sub 2, omega sub 2, omega sub 3, e hat sub 1, I sub 1 minus I sub 3, omega sub 3, omega sub 1, e hat, e sub 2 hat, and plus quantity I sub 2 minus I sub 1, and omega sub 1, omega sub 2, e sub 3 hat. Sorry about that. And the dl dt body, that equals I sub 1 w sub 1 dot e sub 1 hat plus I sub 2 w sub 2 dot and e sub 2 hat plus I sub 3 w sub 3. I'm sorry, why am I saying w? Omega. Sorry, I do that all the time. These are omegas, omega sub 1 dot, omega sub 2 dot, plus I sub 3, omega sub 3 dot, e sub 3 hat. And equating the components gives Euler's equations right here. So here are Euler's equations, standard. Okay, and that is letter A. Okay, moving along to letter B. Letter B, show that kinetic energy is conserved. Okay, so moving along here to letter B. Let's see if this holds. Okay. Conservation of rotational kinetic energy. The rotational kinetic energy is this. T equals that. 1/2 times the quantity I sub 1 omega sub 1 squared plus I sub 2 omega sub 2 squared plus I sub 3 omega sub 3 squared. And taking the derivative there with respect to time, we get I sub 1 omega sub 1 omega sub 1 dot plus I sub 2 omega sub 2 omega sub 2 dot plus I sub 3 omega sub 3 omega sub 3 dot. And if we substitute into Euler's equations, we get the following for dt with derivative here, a capital T with respect to time. Okay, we get this. And now we could rewrite that as the following. And from here, we set this equal to 0. And therefore, we get this d capital T over dt, d lowercase t equals 0. So capital T equals 1/2 times the quantity I sub 1 omega sub 1 squared plus I sub 2 omega sub 2 squared plus I sub 3 omega sub 3 squared. That's going to equal a constant. Okay, so part C. So part C, let's see what they want for part C. For part C, show that angular momentum magnitude is conserved. Okay, so putting this back, let's see if it holds up. Okay, so for part C, conservation of angular momentum magnitude, the squared angular momentum magnitude is that L squared equals I sub 1 squared omega sub 1 squared plus I sub 2 squared omega sub 2 squared plus I sub 3 squared omega sub 3 squared. And then we get this dl squared dt equals 2I sub 1 squared omega sub 1 omega sub 1 dot plus 2I sub 2 squared omega sub 2 dot plus 2I sub 3 squared omega sub 3 dot. If we substitute into Euler's equations, that dl squared dt equals the following. Okay. And the dl squared dt can be written as this. Okay, and then just after we expand, combine, here's what we get. If combining is possible, we set this equal to 0. And yep, we're going to get a nice situation here. dl squared dt, that equals 0. So L squared is equal to I sub 1 squared omega sub 1 squared plus I sub 2 squared omega sub 2 squared plus I sub 3 squared plus, let me start this again. L squared equals I sub 1 squared omega sub 1 squared plus I sub 2 squared omega sub 2 squared plus I sub 3 squared omega sub 3 squared equals constant. Okay, so that is for letter C. And now letter D. Let's see what they want for letter D. Letter D, they want to analyze stability of rotation about the I sub 1 axis. Okay, so let's see if this holds. Okay. All right, so stability of rotation about the smallest principal axis. So steady rotation about the first principal axis here, that lowercase omega sub 1 equals omega. And for this omega sub 2, omega sub 3, that's much less than capital omega. And a more careful perturbation ansatz is omega sub 1 equals a capital omega plus delta omega sub 1. Omega sub 2 equals delta omega sub 2. And omega sub 3 equals delta omega sub 3, where all perturbations are small. And in Euler's first equation, I sub 1 omega sub 1 dot equals quantity I sub 2 minus I sub 1 omega sub 2 omega sub 3. The right-hand side is second order and small perturbations. So the linear order delta dot omega sub 1 equals 0. So the perturbation in omega sub 1 does not drive instability at linear order. The remaining two equations become to first order the following here. So this is the first one, the second one. Sorry about the way I construct the deltas. We're going to find the derivative of the first linearized equation here. Taking that derivative. From there, we're going to use the second equation, substitute this delta dot omega sub 3, and then we're going to get that equal to I sub 1 minus I sub 2 capital omega over I sub 3 delta omega sub 2. So I sub 2 delta double dot omega sub 2 equals the following. And that's a minus sign there, I sub 1 minus I sub 2 in parentheses. So delta double dot omega sub 2 equals this. Okay, and because I sub 3 minus I sub 1 is greater than 0 and I sub 1 minus I sub 2 is less than 0, the product of those has to be negative. The product is negative rather. And we could define here this nu sub 1 squared. That equals I sub 3 minus I sub 1 quantity minus times I sub 2 minus I sub 1 quantity over I sub 2 I sub 3 capital omega squared, and that is greater than 0. So then this delta double dot omega sub 2 equals negative nu squared delta omega squared. Okay. So here, delta omega sub 2 of t is going to equal a cosine of nu sub 1t plus b sine of nu sub 1t, which is bounded which is bounded oscillatory motion. And similarly, delta, sorry about that, delta being drawn that way, delta omega sub 3 is bounded. And we could say from this, so the rotation about the smallest principal axis, I sub 1, is stable. Okay, so that is letter D. And let's see what they want for letter E. Similar type question or statement here. For letter D, analyze the stability. I'm sorry, we just did letter D. I'm sorry. Letter E. Analyze stability of rotation about the I sub 2 axis. Okay, so letter E. Okay. Stability of rotation now about largest principal axis here. So steady rotation mainly about let me change this. Sorry about that. Hopefully this holds up now. Okay. So stability of rotation about the largest principal axis. So the steady motion, steady rotation mainly about the third principal axis here. Omega sub 3 equals capital omega. Omega sub 1, omega sub 2 is much less than capital omega. Use the perturbation and sats omega sub 3 equals capital omega plus delta omega sub 3. We have this for omega sub 1. We have this for omega sub 2. Okay, so to linear order, Euler's third equation gives delta dot omega sub 3 equals 0 because its right hand side is second order and small perturbations. So our first two equations become this. And again, here we're going to take the derivative of that first one. We get the following. We're going to substitute it. And that delta dot omega sub 2 equals this. So our I sub 1 delta double dot omega sub 1 equals the following. And my apologies, that's an I sub 3 minus I sub 1 in parentheses there. And so delta double dot omega sub 1 equals this. All right. And now since I sub 2 minus I sub 3 is less than 0, and I sub 3 minus I sub 1 is greater than 0, the product is negative. So if we define here our nu sub 3 squared, that is going to be this. It is greater than 0. This quantity here is greater than 0. Then delta double dot omega sub 1 is equal to negative nu sub 3 squared delta omega sub 1. So delta omega sub 1 of t equals a cosine of nu cubed, a cosine of nu sub 3t plus b sine of nu sub 3t. So the perturbation remains bounded. So rotation about the largest principal axis, I sub 3, turns out to also be stable. Okay, so I sub 1, I sub 3, stable. Smallest and largest. Okay, of the axes. Okay, so that's letter E. And just going back, now we have letter F. So letter F. Now we want to determine the stability of rotation about the intermediate principal axis. Okay, so and that was letter E. Letter F, analyze stability of rotation about the I sub 2 axis, intermediate principal axis. So from here, consider steady rotation mainly about the second principal axis here. Omega sub 2 equals that capital omega, and omega sub 1, omega sub 3 is much less than capital omega. And we're going to use this for omega sub 2. We're going to use this for omega sub 1, for omega sub 3. And now to linear order, Euler's second equation gives the following delta dot omega sub 2 equals 0. So we have our first and third equations. Finding the derivative of the first equation, we get the following. Okay, we're going to substitute delta, and then delta dot omega sub 3 equals this. And so I sub 1 delta double dot omega sub 1 equals the following here. And so delta double dot omega sub 1 equals this. Okay. Okay, now I sub 2 minus I sub 3 is less than 0, and I sub 1 minus I sub 2 is also less than 0, so the product here is positive. And if we define here gamma squared equals this whole thing, that's greater than 0. So delta double dot omega sub 1 equals gamma squared delta omega sub 1. Okay, from this quotient here times capital omega squared, that being greater than 0. The solution is delta omega sub 1 of t equals ae to the omega t. I'm sorry, let me start this again. That's ae to the gamma t, plus be to the negative gamma t. And the term ae to the gamma t, that's going to grow exponentially unless a equals 0 exactly. So therefore, an arbitrarily small perturbation grows with time. And what we could say for this, the rotation about the intermediate principal axis is unstable. Okay, so that's for letter F. And for letter G, we want to provide a physical explanation for the instability of the intermediate axis rotation. So just so right there. Okay, and here's what we have. Physical interpretation. The torque-free rigid body has two important conserved quantities. T equals 1/2 times this whole quantity, I sub 1, omega sub 1 squared, plus I sub 2, omega sub 2 squared, plus I sub 3, omega sub 3 squared, and L squared equals this. I sub 1 squared, omega sub 1 squared, plus I sub 2 squared, omega sub 2 squared, plus I sub 3 squared, omega sub 3 squared. And the motion in the angular velocity space is constrained to lie on the intersection of the two surfaces, an energy ellipsoid and an angular momentum surface. And then right here we have near the smallest and largest principal axes, the intersection curves are locally closed and stable. Near the intermediate axis, the intersection has a saddle-like structure. This is the geometric origin of the instability, and the smallest and largest principal axes are stable, while the intermediate axis is unstable. And in reference to the intermediate axis theorem, tennis racket theorem. Okay, so that's all for this practice problem, and thank you very much, and have a great day.